In the previous video, we went over a general overview of what the Schmidt decomposition is. We talked about some of its properties, and we also described why is it valuable to represent states in this form. Particularly, we said that when we represent states in their Schmidt decomposition, we can easily see if a state is entangled or separable. And also we discussed that once we have what are known as the Schmidt coefficients, we can build measures of entanglement that actually quantify how entangled a state is. Now in this video, what we're going to go over is how do we compute or how do we derive the Schmidt decomposition of a pure bipartite state. So let's start by recapping what we saw in the previous video. So we said that any pure bipartite state can always be represented in its canonical form, right? Where we have some basis psi sub I on subsystem A and a basis phi sub j on subsystem B. And we can just represent that state as the sum over all of the basis states of both systems. So we're summing over j and I with some complex coefficients Cij. Now the Schmidt decomposition is given by this other form where we're summing over just one index k over the tensor product of sets of orthonormal states u sub k for subsystem A and v sub k for subsystem B, pre-multiplied by this lambda sub k's, which are our Schmidt coefficients. And we also said the Schmidt coefficients are real numbers equal or greater than 0. So an example of this, similar to the ones we described in the previous video, would be something like having the state zeta equal to 1/2 state 0, 0 minus 1/2 0, 1 plus 1/2 1, 0 minus 1/2 1, 1. Right? And this will be represented in the canonical form, like the one we have up here. And again, this will be for A. So here we have a 2-qubit system where the first qubit corresponds to subsystem A and the second qubit for subsystem B. And then again, like in the previous video, we did some Schmidt decomposition examples, but we did the factorization by inspection. And what we will get for the Schmidt decomposition of the state will be the state plus tensor the state minus, and the plus will be for system A, and the minus will be for system B. So here we can see that we have reduced the sum of 4 terms to only 1 term, and then we could say the state was separable. And here our lambda sub k in this particular case will be a 1 here, pre-multiplying this state plus tensor state minus. Now, since this lambda sub k's are pre-multiplying sets of states for subsystem A and subsystem B, that means that the sum of the squares of this lambda sub k's has to add up to 1. And we can interpret this as saying that this lambda sub k's are the probability amplitudes of measuring the state u sub k tensor v sub k. And that would obviously be true if we perform the measurement in this basis, u sub k and v sub k, not in the computational basis. So we're representing the state in a form where we have a sum of some basis states pre-multiplied by this lambda sub k's, which could be expressed as probability amplitudes. Then we also said that this value d, so the total terms in our sum, is going to be given by the minimum of the size of the space of subsystem A and the size of the space of subsystem B, in this case n and m. Now, this will be the total number of summation terms, but some of this lambda sub k's can be 0, right? And you might say, well, wait a second, in this example we have right here, the size of subsystem A, which is 1 qubit, will be 2 to the 1, which is 2. And for subsystem B is also 2 to the 1. Then how come we end up with only 1 term? Well, that's because here we can say that we also have another term equal to state minus, tensored state plus, obviously for A and for B. But here the lambda sub k pre-multiplying this state is just equal to 0. And that brings us to the next important concept when we're talking about the Schmidt decomposition, which is the Schmidt number, also sometimes known as the Schmidt rank. And the Schmidt rank is the total number of lambda sub k's in our Schmidt decomposition different than 0. And we also said that this Schmidt number or Schmidt rank is bounded by d, which is the total number of terms that we have given by this minimum of the spaces, the size of the spaces of A and B. And we also said that it can be as small as 1. And when this Rs is equal to 1, that means our state is separable because we only have one tensor product between two states of the two spaces of interest. And then if this Rs is not 1 but greater than 1, then we say that with certainty the state is entangled. Now, another important thing to reiterate is that these lambda sub k's are extremely important because they give us an idea of how strong of a correlation there is between, let's say, the state U sub k in A and the state V sub k in B. So we can use this lambda sub k's to build measures of entanglement that will tell us how entangled the overall state is. And we'll talk a little bit more about that in future videos. All right, so now let's talk about how do we compute this lambda sub k's, U sub k's, and V sub k's, right? In the previous video, we did this by factorizing our state, but we just did this by inspection. But what is the general procedure that we can follow if we, for example, have a very large state that is not trivial to factorize just by looking at it? So the way to do this is by first starting by representing our state, in this case zeta, in its canonical form. So basically as a linear combination of all basis states in subsystem A, so this psi sub i's, and all basis states in subsystem B, so our phi sub j's, right? So we're going to have some complex coefficients, c sub 0, 0, c sub 0, 1, all the way to c sub n minus 1, n minus 1, which represent all possible combinations of these basis states. And, for example, these basis states could be the computational basis. So in this particular example, let's say we have 1 qubit subsystem for A. So our basis states are state 0 and state 1. And 2 qubit subsystem for B. So our basis states are 0, 0, 0, 1, 1, 0, and 1, 1. So the linear combination in this canonical form is given by this expression here, where we have the basis state 0 for subsystem A, tensor with all the basis states of B, and then the basis state 1, again, tensor with all the basis states of subsystem B. So the next step is, once we have represented our state in its canonical form, is to put these coefficients in a matrix that can be seen as a correlation matrix. So basically we organize them so that the rows of this matrix represent the coefficients of the psi sub i's, and the columns of this matrix represent the coefficients of our phi sub j's, right? So here we will have, these coefficients in the first row correspond to the ones associated with psi 0, and the coefficients in the first column will be all of those associated with the basis state on subsystem B, phi 0. So following the example we had here for subsystem A having 1 qubit and subsystem B 2 qubits, this matrix will be of this form. And taking it one step further, if we want to look at a particular example, for example, a W state where we associate the first qubit with subsystem A and the second 2 qubits with subsystem B, that particular matrix will be given by what's shown down here. Now, what does this matrix represent? Well, we can see this matrix as a map that takes us from the space of subsystem B to the space of subsystem A. So if we were to take this matrix that we call here CAB and apply it to, for example, one of the basis states on subsystem B, well, this is going to just give us the linear combination of all the different basis states in subsystem A associated with phi sub 0. In this particular case, I picked phi sub 0, right? So the result of that will be just basically a column vector given by all these different terms right here, which we can also represent as C00, psi 0 plus C10, psi 1, and so on, all the way to C n-1, 0, psi n-1. So more generally, we could take this matrix and apply it to some arbitrary state in the space of subsystem B. Let's call it, state vector B. And what this is going to give us is some linear combination of states in the space of subsystem A with coefficients associated with whatever this state B is composed of. Now, why would we do this? Why would we construct a matrix that maps states from subsystem B into states in subsystem A? Well, because now that we have this matrix, maybe what we can do is find a series of vectors that are orthonormal in the space of subsystem B, that when we apply this matrix CAB to these vectors, let's call them V sub k, we end up mapping to a series of also orthonormal vectors in the space of subsystem A, so some U sub k's, and maybe perhaps pre-multiply by some constant factor, lambda sub k. And this is exactly what we would need to represent our state in its Schmidt decomposition, right? A series of orthonormal vectors in the space of subsystem B, orthonormal vectors in the space of subsystem A, and then some factors lambda sub k. And if we're going to have a series of vectors, maybe we can represent them in matrix form. So we can take this CAB and multiply by a matrix which is composed of all these different state vectors in the space of subsystem B. So let's call it V0. And this ket is a column vector, right? So this first element in the matrix is the first column of the matrix, and then some V1, which is the second column, all the way to V sub m-1, right? And then we want this to be equal to some series of vectors in the space of subsystem A. So some U0, which is also a column vector, some U1, and then all the way to a U sub n-1, right? And then each of these will have to be pre-multiplied by some coefficients, which we organize in a diagonal matrix, lambda sub 0, lambda sub 1, all the way down to some lambda sub d, which is the minimum between m and n, and then the rest of these coefficients will be just equal to 0, right? So all I'm doing here is just representing in matrix form this expression here for all the different values of k, right? So what we have is that this C sub A is mapping all these different orthonormal vectors in the space of subsystem B to some orthonormal vectors in the space of subsystem A pre-multiplied by some constant, right? And if we reorganize this, or first let's assign some names. Let's call this matrix the matrix V. Let's call this matrix the matrix U, and let's call this matrix the matrix sigma. What we would have is CAB times V equal to U times sigma. And we could then say that we can express this matrix CAB as this U sigma, and then to move this V to the other side of this equation, this will be V transpose. So basically what we're saying here is that now that we have organized the elements of our state in a matrix that we call CAB, we want to express that matrix as three separate matrices, one that is composed of orthonormal states in the space of subsystem A, one that is composed of orthonormal states in the space of subsystem B, and some matrix that links the two of them. And the reason we can do this is because the way we construct this matrix CAB was by placing the coefficients in the rows of the matrix associated with the basis states of the space of subsystem A, and in the columns, the coefficients associated with the states of subsystem B. So there's a way in which we can express things this way. Now, the great thing about this is that this representation is actually known as the singular value decomposition, or the SVD of a matrix. And the SVD is great because it's always guaranteed to exist for any matrix. So once we construct our matrix CAB, we can then perform some linear algebra techniques to extract our U matrix, which will have on its columns our U sub case. Then our V matrix, well, here we will get V transpose, but we just need to transpose it so that the columns of V would be our V sub case. And then the sigma will contain in its diagonal the lambda sub case that link our U sub case to our V sub case. So basically, to recap the steps that we need to follow, first thing we do is we write our state in its canonical form, for example, represented in terms of the computational basis for subsystem A and subsystem B. The next step is we construct the matrix where we place all these coefficients as we have described, where columns are associated with subsystem B, rows are associated with subsystem A. Then we perform the SVD, and then the columns of the U matrix that we obtain are our U sub case, the columns of the matrix V are our V sub case, and the diagonal elements of our matrix sigma are lambda sub case, which are our Schmidt coefficients. Now in linear algebra, this vectors and coefficients are known as the singular vectors and the singular values. Now, the next obvious question is, well, how do we compute the SVD? And I was thinking about going over the most straightforward way to extract these three matrices, but I think it would take way too much time. And what I want to do then is just add some links in the description below to a series of videos specifically on the SVD if you're interested in learning how to do this. So the last thing I want to do is just go over a simple example, an example that we have looked into before, but I want to compute or extract the Schmidt decomposition using this procedure that we describe in this video. So in a previous video, we looked into this W state, right, where we have an equal superposition of the state 0, 0, 1, 0, 1, 0, and 1, 0, 0. And we said, okay, let's associate the first qubit with subsystem A and the second two qubits with subsystem B. So if we were to perform the Schmidt decomposition of this state, the first thing we would do if we were going to do it by inspection is, well, we start factorizing things, right? So this 0 right here is common to these two terms, so we can factor it out. And then the next step that we could do is, if we want to normalize this state on subsystem B, so we can basically add a 1 over root 2 to each of these, right? But if we're taking a 1 over root 2 from this 1 over root 3, then we need to adjust for that, and then our pre-multiplier will be a square root of 2 over 3, right? So basically this state right here is now in its Schmidt form. So we have a state that has a lambda sub 0, which is this root of 2 over 3, a u sub 0, which is our basis state on subsystem A of 0, a v0, which is this equal superposition state of 0, 1, and 1, 0, and then this lambda 1, which is the root 1 over 3, and then our u1 and our v0. And as we can see here, the states in subsystem A are orthogonal, right? So this 0 and this 1 are orthogonal, and or orthonormal. And then this state, this equal superposition of state 0, 1, 1, 0 is also orthonormal to the state 0, 0, right? If we perform the inner product between the two of them, we're going to get 0. So again, we did this by inspection. So now let's follow the procedure that we described to extract the Schmidt decomposition for this state. So I want to do this in Python just because dealing with these matrices can get a little bit tedious. So the first thing I'm going to do is I'm going to use this state vector class from Qiskit just to generate a nice visualization of the state that we're interested in. So here we have that 1 over root 3 of 0, 0, 0, 0, 0, 1, 1, 0, 1, 0, and 1, 0, 0. And in Qiskit, I can just display this nicely in ket notation. But if I take this data attribute, I can get the array that corresponds to the column vector of this. And I'm going to use SymPy just to display that a little bit nicer. So here we have, our column vector, which has this 1 over root 3 for 0, 0, 1, 1 over 3 for 0, 1, 0, and 1 over 3 for 1, 0, 0, right? So the first thing we said we needed to do was to basically construct that matrix C, right? So let's go back here to what we had shown for our example, right? So this state I'm looking into is the same we had looked into before. So this is the matrix that we need to construct, right? Where we have the rows representing the basis states of subsystem A and the columns representing the coefficients associated with subsystem B. So to do that, I can just take this data and reshape it into a 2x4 matrix. So if I do that and then I display it using, let's actually assign this to C. And then if I display this using SymPy, here we can see now we have the same matrix we had here before. And all we need to do now is to perform the SVD on this matrix, and NumPy has a function to do this. So we can assign the matrix U, S for sigma, and VH, which will be our V transpose, to NumPy, and then we use linear algebra, SVD, and all we need to pass is our matrix C. And then here we can set this parameter of full matrices to false. So as we described before, when we perform the SVD, we're going to get that sigma matrix that is going to have in its diagonal our lambda sub k's. And those lambda sub k's are going to go up to lambda sub d, where d is the minimum of the size of subsystem A or subsystem B, and the rest of those diagonal terms are going to be 0. So by setting this full matrices to false, all we're doing is just ignoring all those components that are equal to 0. It's just going to give us matrices of the same size where we have truncated all the terms that will be multiplied by those zeros. Okay, and once we do this, then we can display our matrix U. And here we can see that in its columns, we get the decomposition for the Schmidt vectors in subsystem A. So basically we get state 0 and state 1, which if we go back to our example here, that's precisely what we should be getting, right? So our U0 is supposed to be state 0 and our U1 is supposed to be state 1. Now let's display our matrix VH, but if we want to display our matrix V, what we need to do is take the transpose. So I'm going to do numpy transpose of VH, and we're going to display that. And here the first column has a 1 over root 2 for state 0, 1 and a 1 over root 2 for state 1, 0. And then the second column has a 1, so this will be state 0, 0 because these terms are very small. And if we want to see that a little bit better, we can round this. So let's do a round here to, let's say, 10 significant digits. And here we can see that that second element is just the 0, 0 state. So if we go back here, we can see that our V0 is supposed to be this equal superposition of states 0, 1 and 1, 0, and our V1 is supposed to be the state 0, 0. And lastly, we can display our S matrix or our sigma matrix. And here we see that this corresponds to the diagonal elements of the sigma matrix. So this S is actually a vector. So this numpy function returns S as a vector, not as a matrix, which gives us the diagonal elements that we're interested in. And this 0.81 is our lambda 0, which should be square root of 2 over 3. So if we take, numpy square root of 2 over 3, we get 0.81. And then our lambda 1 is supposed to be square root of 1 over 3, which if we do that here, we can see is equal to 0.577, which is what we get here. So this is the way we will compute the Schmidt decomposition for any state. And here we use this example of a W state, but it could be anything else. Once again, I hope this was helpful, but please let me know if you have any questions.